Today, we're going to pull back the curtain on machine learning. We all see these incredible, almost magical results, but we rarely see the meticulous, crucial prep work that makes it all possible. Trust me, it's not magic, it's work. So let's get our hands dirty and see what's really under the hood.
So what is the big secret? What's the one thing that can make or break a project? Well, it's not some crazy complex algorithm or a giant supercomputer. It's actually something much more fundamental. And it's what data scientists spend the vast majority of their time wrestling with.
And it all comes down to this right here: data pre-processing. It's the unglamorous, behind-the-scenes job of cleaning and preparing your data. Think of it like cooking. If you start with bad ingredients, you're going to get a bad meal. I don't care how fancy your recipe is.
So, first things first. Before we can fix the problem, we have to understand the beast we're trying to tame. And that beast is real-world data, which, let me tell you, is almost never neat and tidy.
You'll hear people call real-world data dirty, and this is what they mean. It can be incomplete, like a form where someone forgot to write their occupation. It can be noisy, which just means it has errors, like a negative number in a salary column. And it's often inconsistent, where the same thing is recorded in a bunch of different ways. This is the mess we have to clean up.
Okay, check this out. This is a perfect example of what noisy data looks like. Just look at row 7. The duration is 450. Now, every other value in that column is somewhere between 30 and 60. That 450 isn't just a little high, it's a massive outlier that could totally confuse our model if we don't handle it.
So, we get it. The data's messy. But why exactly is cleaning it so important? Well, it goes right to the heart of what machine learning is trying to do in the first place.
You see, at its core, machine learning is all about letting a computer find patterns in data all by itself. And the key word there is data. The machine learning model is only ever going to be as good as the data it learns from.
And this is really the bottom line. Most algorithms will just crash if they hit an empty cell. They have no idea what red or green means. They only speak numbers. They can get totally thrown off by features that have wildly different scales. And most importantly, it boils down to this: garbage in, garbage out. You feed a model junk, you're going to get junk predictions. It's that simple.
All right, let's get into it. Our first challenge on this data cleaning quest is tackling those empty cells. What do we actually do when our data has gaps?
We've got two main strategies here. The simplest one, just delete the rows with missing data. But you have to be careful, you might be throwing away really valuable information. A much smarter approach is what's called imputation. That's where we fill in the blanks, usually with a calculated value like the average for that entire column.
Okay, so we filled in the gaps. Our data is complete, but we have another problem. Our model still can't read it because it's full of words. We have to translate all of those categories into the one language a computer truly understands: numbers.
There are two popular ways to do this. The first is label encoding. It's super simple. Red becomes 0, green becomes 1, blue becomes 2. But there's a hidden trap. Your model might start to think that blue, because it's a 2, is somehow bigger or better than green, which is a 1. For categories that don't have a natural order, a method called one-hot encoding is way safer because it avoids this problem completely.
And here's what that one-hot encoding looks like. See how that single animal column just explodes into a whole new set of columns, one for each animal? A 1 means, yep, this is a dog, and a 0 means, nope. Now every single category is treated as an equal, and our model can get to work without making any weird assumptions.
We are on a roll. We've dealt with missing data, and we've translated our text. Now it's time for our final major challenge: making sure all our different features are on a level playing field.
And this is where things get really interesting. See, a lot of models work by measuring the distance between data points. But if you're comparing salary and age without making any changes, the huge numbers from the salary column will totally dominate the math. A $35,000 difference, when it gets squared, becomes a massive 12 million. That age difference of 23? It's just 529. The model will basically think salary is the only thing that matters, just because the numbers are bigger.
To fix this, we scale our features. One way is normalization, which basically squishes all the values into a nice, tidy range between 0 and 1. Another popular method is standardization. This one reshuffles the data so that the average is 0. This is usually a better choice if your data has some of those crazy outliers, like that 450-minute duration we saw earlier.
All right, time for a quick bonus round. What happens if you have too many features? After you do that one-hot encoding, you could suddenly have hundreds of columns.
This can make your model slow, clunky, and inefficient.
Well, there's a powerful technique called principal component analysis, or PCA, that can help. Now, it sounds super complex, but the main idea is actually pretty simple. It's about summarizing your data. It looks at all your features, figures out the most important underlying patterns, and then creates a new, smaller set of super features that capture most of the original information, but with way less clutter.
So after all of that cleaning and translating and scaling, we've reached the end of our data preparation journey.
And this is what we're left with, a beautiful, pristine data set. It's got no missing values, it's completely numerical, all the features are on the same scale, and it is finally ready for the main event, to be fed into a powerful, accurate machine learning model.
And that brings us right back to our main point. So much of what makes machine learning successful doesn't come from picking the fanciest, most cutting-edge algorithm. It comes from the careful, thoughtful, and yes, sometimes difficult, work of getting the data just right.
All of this work, all of this preparation has brought us to the starting line. Our ingredients are perfect. The next step is to finally start cooking and build the model itself. But well, that's a story for another time. Thanks for joining me.